let's start our next topic. This is section 4.8, Newton's method. This kind of reminds me a bit of section 310, linear approximation and differentials. Number 1, because it's an approximation. Number 2, because it's an application of the derivative. And number 3, because it actually does use linear approximation a little bit. The explicit formula might not look like it so much, but to derive it, we use linear approximation. Let me motivate this a bit first, then I'll derive the formula, then I'll just give you the formula, and we'll do some examples. When you type a number into a calculator, like the square root of 3, the calculator doesn't actually give you the right answer, right? It gives you the best possible approximation given the number of decimals it's allowed to go out, right? We all know that the square roots of non-squares are irrational, right? They never start repeating. You can't properly express them as decimals or fractions. So we just have to settle for really good approximations, right? And so, for example, if you type in the square root of 3 into your calculator, you're going to get the following. I actually typed this into Google, and I got the following. Okay, so again, that's not the right answer, but it's a very good approximation. And so the goal is, the question is, how do they get that, right? The goal is to replicate that, right? So it turns out most calculators use an algorithmic estimation technique called Newton's method. You might also hear referred to as the Newton-Raphson method. Now, let's recall that a 0 of a function, or you might hear it as the root of a polynomial, right, if it's a polynomial. But the 0 of a function is a value a such that f of a equals 0. So, for example, if we wanted to find all zeros of this function, right, well, one method is called guess and check, right? If you know the rational root theorem, you know that all the rational roots anyway, have to divide 6. So plus minus 1, plus minus 2, plus minus 3, plus minus 6. So let's just try. F of 1, well, that's going to be 1 cubed. Minus 7 times 1 plus 6. Oh, look, that equals 0. Yay. F of 2. 2 cubed. Minus 7 times 2 plus 6. Oh, look, that equals 0. Okay, look, we've already found 2 zeros. F of 3. 3 cubed, that's 27. Minus 7 times 3. That's it. Oh, we're plus 6. No. Maybe f of negative 3 might work. Oh, look, that does equal 0. Yes. So, in this case, f, maybe I'll call it f of x, I guess you could say, has zeros. X equals 1, 2, and negative 3. Now, these zeros are about as nice as it gets, right? They were whole numbers. They were easy to find. A lot of times, even with polynomials, like even with cubics, it doesn't work out so nicely, and it's not so obvious what the right answer is, right? Or maybe you do know what the right answer is, like in the case of the square root of 3, but you don't really know how to express it properly. Like you just write it as a radical 3, but you don't know how to write it as a decimal. So let's alleviate that, right? Here's the way that we derive Newton's method. Let me draw a picture of what's happening first. Consider a set of axes. Whoop. Well, no, that's definitely a y, okay? Now consider some kind of a curve, maybe like this or something. Right? And this is where our 0 is, right there. That's our special point that we're really trying to get to. Well, what we can do is we can use the tangent line to approximate the curve. Now, I hope that's familiar because that's what we did with linear approximation. So suppose we choose some value a, right? And we're going to let this be, we're going to call this x1, right? So we just look and we see, oh, okay, there's the function, right? There's the curve, rather, and right? There's our tangent line, right? Now, the idea is, right, we don't know exactly where the curve equals 0, but we do know where this tangent line equals 0. That should be a pretty nice value. We'll call that x2, right? And then we can say, well, I guess we could just sort of repeat this process, right? We just kind of go up here, draw our tangent line. Maybe make that a little bit better and approximate. There we go, right there. And we can say, oh, where does this guy equal 0? And then we can just kind of wash, rinse, and repeat this process, you see? And as you notice, we get closer and closer to our desired value. Maybe just call this guy x or something like that, right? We're getting closer and closer to x by just iterating this process. And all we're doing is we're using tangent lines and finding the zeros of these tangent lines again and again and again. I don't know why I did all that nonsense. I didn't need to. Okay. Maybe I'll move this over a little bit or something. There we go. All right, so anyway, that's what we're doing. Now the question is, how do you write that in math, right? I drew a picture. How can we convert that to an actual function, right? Well, so suppose that we have a function f of x with a 0, a. Oh, they're calling it the 0, a? Okay, well then we'll call this x1, and I guess this is called a. Okay, anyway, we find an x value x1 that is nice, so to speak. And all else even, you want it to be near a. Okay? We want to find the value where the linear approximation of f at x1 equals 0. We'll call it x2. In other words, for the equation, L of x equals, maybe I should say for the function, really. For the linearization, L of x equals f of x1 plus f prime of x1 times x minus x1, right? Notice that that's just the linearization of f at x1. We find x2 such that, L of x2, which of course equals f of x1 plus f prime of x1 times x2 minus x1 equals 0. Now, if you do the arithmetic out, I'm going to just do this really quickly on the side of the page because I didn't leave a ton of space for this. Find x2 such that L of x2 equals 0. Well, what's that going to be? F of x1 plus f prime of x1 times x2 minus x1 equals 0. You should be able to solve this, no problem, right? Subtract over the x1, the f of x1, right? We get f prime of x1 times x2 minus x1 equals negative f of x1. Divide by f prime. x2 minus x1 equals negative f of x1 over f prime of x1. And then just add over the x1, and we get x2 equals x1 minus f of x1 over f prime of x1. Whew. All right, so I'm just going to write all that over here, right? So I'll say, i.e., find, and I'll just move this over a little bit here, x2 equals x1 minus f of x1 all over f prime of x1. Okay? That's what you're really doing. I'll move this up just to be a little... What the... Okay. And then, so that's how we found x2, right? But then if we want to find x3, we just kind of do that all over again. Replace x1 with x2. And then replace what was x2 with x3. And we just keep doing that as many times as we want until our approximation is as good as we want it to be. Right, so eventually we'll get arbitrarily close to A. If you want a better approximation for A, then just keep iterating the process or the algorithm. right? This process is called an algorithm. So, for example, use Newton's method to approximate the square root of 3 as well as the calculator does. I'm not going to do that right here. I'll do the first couple of steps, but you'll see even after 2 steps, it's a pretty good approximation, right? So what we're going to do here, if I give you a problem like this, you need to come up with f of x. Just like if I said approximate 3.99 squared for a linear approximation problem, you'd have to be like, ooh, f of x equals x squared. Well, here what we're going to do is we're going to say, all right, let x equal the square root of 3. I'll move this down a little bit here. So x squared equals 3. See how I just squared both sides? So remember, we're interested in the zeros of a function, right? So x squared minus 3 equals 0. So let f of x equal x squared minus 3, right? And now we're interested in the zero and finding the zeros of f. This is where we want to be. You want to find the function such that when you properly approximate the value, you're getting really close to 0. So if you remember, the square root of 3 is between 1 and 2. It's closer to 2, so I'm going to use 2, right? Let x1 equal 2. You can let it equal 1. You can let it equal 1. It's totally fine. You might get slightly different answers from me, but eventually you'll get a good approximation. Might take an extra step, right? Sorry, there's a bug on my iPad. Oh, okay, went away. So anyway, let x1 equal 2. So using Newton's method, we get x2 is going to equal, well, remember, it's x1 minus f of x1 all over f prime of x1. And if you forget that, then just remember, it's where the linear approximation at x1, at 2, right, in this case, equals 0. Right, so we're going to get 2 minus f of 2, which is 2 squared minus 3, all over, let's do this out right here, f prime of x equals 2x, right? So this is going to be 2 times 2. So this winds up being 2 minus 1/4, and we wind up getting 7/4, or 1.75. And notice already, even after one iteration of Newton's method, we're actually somewhat close to a decent approximate, right, to the square root of 3, right? 1.75, right? That's what we get after one iteration. That's pretty close. It's pretty close, excuse me. Now, if we want to get closer, right, if we're fine with that, then we're done. If we want to get within a tenth, then we're done. But if we wanted to get within a hundredth, then we say, well, we better do this again. So at this point, we let x2 equal 7/4, okay? So x3 is going to equal, well, that's going to be x2 minus f of x2 all over f prime of x2. And that's going to be 7/4. You note that the arithmetic gets a little nastier here. 7/4 minus, well, I guess it's going to be 7/4 squared minus 3 all over 2 times 7/4. See how I just plugged it into f and f prime? Anyway, when you do the arithmetic out, just trust me on this one, you wind up getting 97/56. Write that on the meter. Okay? And if you put that into a calculator, you get this. And this is reasonably close to the square root of 3, right? Oh, sorry, I just wanted to copy this. Copy, copy, copy. So if you just take a look, we've done Newton's method only twice, and we get the same answer up to the nearest thousandth, right? We're good up to the nearest thousandth. In fact, we're really within 1/10,000th, if you take a look. Okay? So maybe you can just trust that if we continue to do this over and over again, we would get the right answer. We would get an answer as good as the calculator's answer, right? And it would never be perfect. It would always be a fraction, but we would get the right. We would converge to the right answer, right? Now, just to be clear, what we were doing was instead of doing the whole find the linear approximation, set it equal to 0, solve for x2, I just straight up solved for x2 every single time, right? Right, and then in this case, right, I just solve for x3, right? It equals x2 minus f of x2 over f prime of x2. And then xn equals xn minus 1 minus f of xn minus 1 all over f prime of xn minus 1. So in general, what is Newton's method? And this is what the book says, right? Given a function f of x with 0a, we let x1 be near a. Then xn plus 1 equals xn minus f of xn all over f prime of xn. Okay? So that's how you do it. And I'm pretty sure that's how the book writes it. Okay? Now, I'll just say the value x1 matters. Usually, you've got quite a range for what to choose, but, choose it close to a. And for technical reasons, right, if you choose it on sort of the wrong side of the curve, it could give you a weird answer. Here's a kind of a funny example. Try approximating this guy for any x1 not equal to 0, right? Now, this is kind of a weird one because we know that the right answer is x equals 0, right? But we're going to let f of x equal the cube root of x. Okay? Let's just go over here, right? Do this on the side here. So we'll say let x1 equal 1. Harmless enough, right? Pretty close to 0. So I guess x2 is, well, I guess if x of x equals that, so I guess we get that f prime of x, right? We're going to need that. 2 is going to be 1 over 3 times the cube root of x squared. All right, so let's see. x2 is going to equal, it's going to be x1 minus f of x1 all over this guy. All right, and then let's see what this equals. This is 1 minus 1 over 1/3, which is 1 minus 3, which equals negative 2. Okay, well, that's a little weird. We started at 1, and then we went to negative 2. That's actually further away from what we wanted. Right, we know the answer is 0. Let's try one more. Let x2 equal negative 2. So x3 is going to equal negative 2 minus, I guess it's going to be the cube root of negative 2 all over 1 over 3 times the cube root of negative 2 squared. And if you do that out, you're going to get negative 2 minus, well, if you think about it, this is actually going to be 3 times negative 2, which equals 4. What? So we went from 1 to negative 2 to 4. So let's see what on earth is going on here. We draw a set of axes. Okay, all right, looks like these are going to need to be a little bit wider, right? X-axis, y-axis. We've got the curve cube root of x equals 0, right? And that looks something like this. Something like that. Okay, so, and really it should probably be even more vertical like that, but whatever. Anyway, we started at 1. But then when we drew the tangent line, well, where did that equal 0? It equaled 0 way over here at -2, right? So when x1 equaled 1, we got that x2 equaled -2. All right, and then, let's see. We had here, maybe I'll even do this in blue, actually. Maybe I'll do it in black. We found the tangent line for this guy, and that wound up being there. At 4. Right? So you see what's happening. This just doesn't work well with every curve. Right? Now, again, this is kind of an arbitrary sort of made-up one, right? Because we didn't need an approximation for this one. But it's just to show you that this kind of thing can happen. Here's another example, right? Approximate the root of the equation for this function, f of x equals x cubed minus 3x plus 6, by first choosing x1 equals 1. I don't know, seems like a pretty reasonable guess. Let's try it. Let x1 equal 1. We should also note that f prime of x is going to equal 3x squared minus 3. Okay? So I guess that means that x2 is going to equal x1 minus f of x1. Okay. Over f prime of 1. Well, that's all good, except that we're going to get 1 minus, is it 7 minus 3? 4 over 0. Right? So, you see, that's just not happening. And what that suggests is that the tangent line to f prime at that value will not equal 0. Why did this method fail? Because the tangent line to f, or maybe I should say to y equal f of x at x1 equals 1 is horizontal and has no zeros. What? So what value should we choose instead? Well, I don't know. Look at a graph, right? But if I plug in 2, that gets, well, does that really get me even closer? No, it doesn't, actually. It gets me further away. What if I plugged in -1? Yeah, that might be better. Let's try x1 equal -1, right? Now let's approximate correctly to 2 decimal places, right? So, let's see. Let x1 equal 1. So, sorry, not 1. -1. So x2 is going to equal -1 minus -1 cubed minus 3 times -1 plus 6 all over now f prime of -1. Oh, actually, wait, that's not going to give us any better an answer, is it? Yeah, Right, because it's still going to give us 0, isn't it? Is -2 going to be a better guess? Yeah, let's try x equals -2. Let's try that. x1 equal -2, so x2... There we go. Sorry about that, guys. Let's try that. And then f prime of negative 2 is going to be 3 times negative 2 squared minus 3. And then this will give us negative 2 minus... and then this is negative 8 plus 6 all over, was that 9? Yeah. Negative 2 minus 4/9. Alright, and then that's going to equal negative 22/9. Right? Let x3, or sorry, I should say let x2 equal negative 22/9. So x3 equals blah, blah, blah. You can see pretty quickly that you're going to need a calculator to do this effectively, which you could say kind of defeats the whole point of it, but just to show you that there is a process to approximate the zero function, okay? So I'll let you do this once or twice more. When your answer is basically the same, has the same first few decimal points, that's when you know that it's a good approximation, right? You've approximated to that many decimal points. So just to be clear, on a quiz or an exam, I would not be able to give you a question that required a calculator, so I'd probably say something like, do Newton's method twice and see what you get.